Okay. Everybody knows who I am, right? So we're gonna start with this presentation: useful can-can soccer algorithms. I'm trying to encourage everybody and every team to be successful, and so I'm trying to share some information here that might be tricky. I'm not going to show you the way. I'm going to show you a way. And that's a big difference. You may see things here that you know how to do better. All the power to you. That's your competitive edge. If you're looking at this and you're saying, well, I never thought about that, then this is for you. Okay? So let's, let me see here. Page down. Yeah. Okay, so I've got the purpose today to do two things. One, to show you some useful algorithms, and then also impart some lessons learned that I have had since I've joined DPRG. All right. Okay. Now let's start with the problem. So the problem is we got this 7-foot by 10-foot arena, and you got an opposing robot, and you got 6 cans in the middle, and your job is to push as many of those cans through his goal before he pushes too many through your goal. You can't be aggressive. That's against the rules. So there's no ramming, no chainsaws, not even ground thumpers or anything. So it's straight robot against robot from a point of view of gathering cans. And what the extra robot does is it provides a little bit of randomization of the problem. All right, so what you got to do is you got to go find the can, capture the can, and take the can to the goal, and repeat that as many times as you can in 10 minutes. All right. So there's a couple questions. How do I find a can? Is it a can or a wall or even a robot? How do I capture a can? Well, there's different ways, but I'm going to talk about not claws and not scoops. I'm going to be talking about another aspect of capturing. And then we're going to, how do you find the goal? So there you got to know where you are and where the goal is. So first we're going to start with some simplified differential robotic kinetics. But what I'm really doing with this, don't get too hung up on the equations. We'll go through them in a second. It turned out that a differential robot, the equations are pretty simple. But what I really wanted to do with this picture is to show you what the terms are, so that when you look at the program that I'm going to show you in a little bit, you can kind of understand, well, what does he mean by heading error? What does he mean by distance to target? You'll know those things when we get finished with this. Okay, now this is the way, if you go out on the internet and you look around, this is usually the way everything is defined. I use Dave Anderson, where he went. Oh, there he is. Dave has a wonderful site that goes through this, and that was how I first made my first navigating robot. And to do that, this is the way, I'll call it the Dave way of looking at things. And what you'll see here, I've outlined in red things that are different from the previous foil. And essentially what he did, and it's because I think of historic reasons for boats and ships, and ships always went Y instead of X. So, right, Dave? Yeah, so 0 theta is the Y direction. Where when you go on the internet and look around, a lot of times 0 theta is in the X direction. So if you're looking around and you're using Dave's site and you start to get confused because things are a little bit different. So let's look at since this is where we're going to go, let's look at the equations here. Okay, the first thing that they say is that the average displacement, so they've taken this linear velocity and changed it into a displacement, and they say the left wheel displacement plus the right wheel displacement divided by 2. Now what does that mean? That means the encoder counts on your left wheel and the encoder counts on your right wheel are averaged for an increment in time. Okay? And that's the amount of distance that you moved. Alright? Now theta is the angle. Alright? And this is different. I've highlighted in red what's different from the previous foil. So you're going to take the left wheel displacement, which is the encoder counts on the left wheel. Actually, it's for the increment of time that you're looking at. Minus the encoder counts on your right wheel, the increment of time you're looking at, divided by the wheelbase. And then,
counts in revolution? Is that wheelbase?
no, it's actual ticks.
Oh, okay.
Okay.
I think
Now, but we're not going to talk in ticks. We're going to talk in ticks per inches, I believe. So we're actually talking. The units will be inches. Okay. And you'll see that when I start showing the program. Okay. All right. Good catch. X and Y. So X and Y. If you think of the average displacement as the magnitude of the vector. A vector has a magnitude and direction, and you multiply it by the angles in either the sine or the cosine to divide it into x and y, and you keep track. And remember, you see this is one thing I want to make sure you're noticing. Since you're doing this for little increments of time, you're keeping track of it, because it's not going to help you much if you only know you moved a ½ inch this time. If you don't remember you moved a ½ inch last time and a ½ inch the time before. You know, you have to keep track of x and y and where theta is changing. All right? Okay, I'm not going to go into this. This presentation is going to be out on the web. I want you to be aware that this is up there, and this is just to help you along. The one thing that you probably want to know is that the arctangent is kind of weird, okay? And that's why you're going to see in the programs a little later what seems a little complicated. It's not really complicated, but it's trying to handle this weirdness of the arctangent. All right. So I'm going to tell you guys that with 3 small routines and 2 constants, you can do something that you've probably never done before. Well, some of you haven't ever done before. You can take your little wandering robot and turn it into a true navigation. And these routines are all going to fit on each routine on a single page on this program, so they're not very big. All right, so let's take a look at the first one. The first one, we take in the encoder counts. We define left inches is what this is. It's not left in, it's left inches. And it defines an interval count divided by some constant called motor 1 ticks per inch. All right, and you do this by, usually when you buy an encoder, it'll say something like 3,000 ticks per 1 revolution. And if you put a 3-inch wheel, you know, you figure out what the circumference is, and then divide that and figure out how many ticks you have to go to an inch of circumference. That's a good starting place. That may not be the exact place that the number you're going to use. You may end up adjusting that slightly because a lot of people lie. All right, when they say 3,000 ticks per revolution, they may really mean 2,986 or something weird like that. And then your wheel might not really be 3 inches. It might be 3 inches and a tenth of an inch. So when you get it all said and done, you'll probably. But those are good, you know, if you think you got a 3-inch wheel and you think you got 3,000 per revolution, that's a good place to start, but you'll have to tune it. Now, the next thing we're going to do is, hey, wait a minute, this is the left end plus the right end divided by 2, and it gives the average number of inches that you moved, see? Remember that equation on the previous foil? All right, remember this one? Theta is the cumulative number of the left inch minus the right inch divided by the wheelbase. You saw that equation before? All right. Let's see. Okay, now here you have to clip it because you could end up thinking, you might get a number like 360, 390 degrees. And instead of thinking of it as 390 degrees, we want to really think of it as 30 degrees. Okay? So we're going to limit it to 2 pi. And since we're talking in radians, 2 pi radians equals 1 revolution. All right? Then we're going to take the inches that we calculated up here times the sine of theta to get our x position. And remember, we're adding to it. And the same thing with the y position. And so the constants we need are the wheelbase and the motor ticks per inch. So with those two, this is your basic navigation or odometry subroutine. And like I said, a lot of credit to this goes, I learned through going through Dave's site. Okay. Now, there's something here I want to take a look at. I'm going to go back to here.
Is that Dave's site on the bottom of that one page?
Yeah. Dave's got a couple of sites. One about Seattle Robotics and then one out in
in the interest of full disclosure, I got all that stuff from the Johann Borenstein site at University of Michigan.
Okay. So, but the thing that I wanted to say here, I want you to start looking at the equations and thinking about them. All right. When you're going to find when you make a navigating robot, if you're off in the going forward by a ½ inch, you're probably not going to worry about it. But if you're off 1/10 of a degree, you're in trouble. Okay? So let's think about that. In theta here, okay, it's equal to, so in a perfect world, my encoder counts would both have the same count, right? So that the difference between them would be 0, right? And my theta wouldn't change. But if I did have a difference between the two of them, what happens with the wheelbase? What if I have a small wheelbase or I have a big wheelbase? If I have a small wheelbase and I have a difference, it's going to mean a bigger change in theta. So since you can kind of keep your from an encoder's point of view, it doesn't matter. Every time slice you're going to get the same different number. So what you want to do is have a bigger wheelbase so that the difference in theta is smaller. So that I'm just trying to do this so you can see this and kind of think about these equations and not just throw them through. Okay, now let's slide back down through here. Okay, so the next one you need is, you remember that guy, that picture of the can up in the corner? Well, we got to go find him. So if we look at that picture again, you'll see that the x target minus the x position is the x that we need, okay? And the same with the y. Now, you know Pythagorean's theorem, x squared, y squared, just take the square root of it, and what do you have? You have the hypotenuse, right? But you also have the magnitude of the vector from where you are to where the can is. Okay? So we don't allow, remember I told you about the arctangent going to get in here and get in the way? This here is to make sure that you don't end up dividing by 0. All right? Now, the heading error, and then if you have that picture that we had on 2 slides before, it's equal to the target bearing, which was the guy up there by the can, minus the theta that's down by where your robot is. Okay? And they're both referenced to the world frame. Okay? So the heading error is going to give you the difference between those two. Then, again, we're going to take a look at the error, and if it's, let's see, if it's less than pi, greater than pi, then we're going to subtract 2 pi from it. Else, if it's less than minus pi, and this again is handling this, what do we do with the arctangent? All right? Now the last line there is because Doug doesn't think real good in radians. I never, to me it's sort of like metric. Yeah, I understand it, but. So I always put things in degrees, which I use some of the time. Anytime you make a conversion from a unit to another unit, you lose a little bit. All right? But like when I'm displaying how far I'm off, I really don't want to know when I'm off 0.62 radians because I don't know what that means. But if it says I'm 22 degrees off, I can say, hey, I know what I'm at, figure out what's going on. All right, so that's why that's there. All right. Now the third, I promised you 3. And this one's even shorter. This is the delta of the target. And all this is really doing is says, keep on keeping on until you get close enough where I'm saying you're there. And I don't even think we need these. Okay, now with these 3 functions, you know where you are. You know the direction of your target, and you know if you get there. Okay? However, you don't know how to get there. All right? You know kind of where you are, but I'm just standing here, how do I get there? So we'll go through that next. Let's see, was there anything else? I'm sure it'll come to me later.
Well, I had a question. In one of the slides, you had a word wheelbase, and it was actually the distance between the two wheels, not the...
It is actually, okay, that's a good point. What is the wheelbase? The wheelbase is from the center of this wheel to the center of this wheel. All right?
Yeah.
And when we talk about tuning, I'm going to talk about that in a little more detail. All right, but that's your, so in this case where there's fairly wide wheels, measuring from inside to inside is going to be wrong. Okay? Because in a differential robot, the kinetics, the degrees of freedom they think you have, is you don't have any steering, you can rotate forward and backwards, and you can swivel on the wheel. Okay? But there's no slip. Okay? All right, now, okay, where were we? Okay, controlling the motors. All right. Now, most of you have probably heard of a PID controller. No. And I'm going to show you something a little different. This is actually, when you really sit down and wrap your mind around it, it's a PI controller. But it's not a PI controller in the classic sense that you have the little equation where you have the proportional section, and then you have the integration section, and you have this. Because what I'm doing is I'm using the cumulative, I'm using theta. Remember we got theta, which is the current angle where I am. And I'm using that compared to where I want to be as an integrated error in the rotation. Okay, so this is a little different, but it's not that different. It works. You may want to go to a PID, more classical PID. I don't care, But this, you ought to give this a shot, okay, and see if it works for you, because it's real simple. All right. So the first thing I do is I say, if my theta from where I want to be and my real theta is greater than 15 degrees, turn on the rotation in place flag. So what I'm really saying is if the error is too great, I'm going to pivot turn. All right.
Does that mean drive one wheel backwards? And
one wheel backwards, one wheel forwards. Now, do I have to use this? No. But if I suddenly I'm watching this way, and all of a sudden I get the direction, go that way. Well, you know what's going to happen if I don't do this? I mean, if I'm only going a foot, I may go 10 feet before I actually turn to the right angle and then I'm off. And will it find it? Yeah, it'll find it. It will go back. It will get to that waypoint, but it's going to be kind of weird looking. It's much better to go in and say, well, you want to go that way? And go. All right? Now, if you notice here, one says, well, turn it on when you're 15 degrees, and the other one says, turn it off when you're at 3 degrees. Why? That's hysteresis. That's so you don't go boing, 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 boing. So when you turn it on, it's usually because you want to do a big turn. All right? And it'll stay on until you're within 3 degrees. Then the proportional controller is going to kick in. The PI controller is going to kick in and take it that last little 3 degrees. Okay? All right? And likewise, if I went to 4 degrees, I still try to handle it with my controller. And I don't really want to go to the pivot until I'm about 15 degrees. Realistically, most often, you'll find that you really want to make a big turn. Okay? But these are numbers that kind of work. You can adjust them. It's not a big deal. All right? And now, if it says, now here's where it gets a little weird. It says if the heading error is less than 0, then the reference is equal to the minus the degree heading. Remember, that's theta. Okay? And what I'm doing here is I'm changing the reference. If I'm going in a straight line, what I want is I want both encoders to be matched, because I want the difference of them to be 0, because my reference is 0. I'm going in a straight line. I don't want a difference between the encoder counts. All right. But what I'm saying here is throw in, if I've got an error, they didn't do, I'm saying throw in the theta, and I'm going to use the theta to bring me back to that position. Okay? So, and then the error is equal to, and you can look at these comments, you can see I didn't trust my memory at all. One motor's negative, one motor's positive. How do I, which one is positive and which one's negative? These are all handling that. All right. Now this is the actual, just little motor controller, and all this is a proportional motor controller. So it only has, it says the correction is equal to some constant times the error. All right, now, you might think of this also as a staged controller, but I'm still wrapping my mind about how I want to think about this. But anyway, just use this proportional portion. So first thing you do is you make sure that you don't get some illegal number, because usually it'll just wrap around. So like if you get 315, you really get minus 315 minus 255, whatever that is. So you don't want to do that. So you limit it. That's the first step. Then you check if the flag is on. And if the flag is on, I just turn the speed at the half. You say, well, that's not even regulated. I'm just saying go. Well, that's because I'm also watching theta. So when I take my intervals, it's going to know that when I'm off, because I'm really trying to drive theta to the value that I want. I'm not really trying to drive speed to what I want. I'm trying to drive theta to what I want. If the rotation flag is off, then it does pretty much what you would normally consider. It adds the correction to one motor, or it takes it away from the other motor to do a little bit of turning. Okay?
So kind of at that point, I guess it's not really a proportional controller, you're just saying, one wheel, this is your speed, this is your other speed, so you're kind of turning
if the flag is on.
Right.
If the flag is on, then I've pretty much said, I'm going to just look at the theta part.
Okay.
Okay.
And you're going to rotate it at fixed speed.
Right. But remember, that's because I've got a big theta difference. Right. So in there, I'm not really curing too much. Okay. Now, once it gets close, then I start curing again. Mm-hmm. Okay? Mm-hmm. Like I say, there will be some of you in here who say, well, I can do that better. That's your competitive advantage, guys. I'm glad for you. Okay. All right, now some tuning. All right, you got to have these. You got to have accurate encoder counts per inch, and you got to have an accurate wheelbase. How accurate? Real accurate. Okay. Remember, I told you 1/10 of a degree, you're probably toast. But you know, you don't want it. Okay. So this means, this is a rule here. Anytime you futz with the wheels, you got to retune. People may remember that last year's competition when I was doing tabletop, and at the very end, the last step, he'd lost it. He just was, his theta was completely gone, and he kind of just ran off the table. That was because about a week before, I'd messed with the wheels, had not adjusted it. When I did my post-competition, what in the world happened? I was able to quickly find out where the problem was. All right. So, here's, if you futz with the wheels, now what does that mean? That means if you take the motor out, have you futzed with the wheels? Yes, you have. Does that mean you take the wheels off the hub? Yes, you've done it. Okay? You know, it means if you clean the wheels, that one might be a little, that depends on how dirty they were, I guess. That one I might not. But anything that changes that wheelbase value, so that you tightened up the set screw, you got to go retune it. Okay? All right? Okay, now, one way to tune your robot is described here and on the DPRG work thing by Paul, who essentially did a review of this paper. And then that's where you do the square one direction and you go the square the other direction, and you know, it's very interesting. I'm going to show you what I consider a quicker way, and it seems to work. The science behind it is not as rigorous. It's not as rigorous as the paper, but it seems to work. Okay, the first thing you do is, and you only have to do this once, hopefully, is you want to make sure that your encoders are the same and that they're behaving about the same. So what you do is you put a wheel on your encoder, you mark the wheel, you set it in the air so it doesn't have any load on it, and you rotate it 10 times. And you know where it stopped. Then you rotate it 10 times again and you know where it stopped. It should always stop in the same place. Alright? If left wheel stops and one, you know, rotates and has one thing and the right one is different, then probably you've got different encoders on the wheels. Since a lot of us buy surplus parts, that is a possibility. Okay? So I'm just letting you know that. That's one thing, yeah?
That also shows you if your encoder routine is dropping ticks, which I've seen as a problem.
Yeah, that can happen too. And a lot of them, like for example, a lot of the smart encoders that you see on Vex and Legos, stopping on a dime for them, getting you know, you ask for 100, but you might not get 100. You might get 110, or you might get 90. Okay, and that varies a little bit because there's latency in the way they communicate with the little microprocessor that's on the motor block. All right, but the real thing is that, yes.
Couldn't you just turn the wheels by hand and not?
Sure. Yeah, that's possible too.
Yeah.
I just like to run the motor. Okay. But you're right. You can do that. You can. The thing about running it, Richard, is you can literally say go, if it's 300 RPM, 300 ticks per RPM. I can say go 3,000.
Yeah.
And I don't have to do anything. So I'm just saying that's the way I would do it. Okay, like I say, at this point, all you really want to know is that they're working similarly. The next thing you want to do is you want to see, you know, like, okay, it said it had 300 ticks per revolution, you know. That means if I went X number of things, I'm using this size of wheel, it should go this far. So you take 2 pieces of tape and you put them on the ground and you send it on its way. And now you say, well, what about the wheelbase? Well, hopefully you've taken a ruler and got kind of a rough number for your wheelbase. All right, you know, you took a ruler and you said, ah, it's this, and you put it in there. So you've got a number in there, but it's probably not right. Then what you're going to see is something like this. Okay? Now, then at this point, you can actually change the wheelbase number a little bit, and you can see it go from this red line to this red line. Now, whether you add to it or subtract to it, I don't remember. Okay, but you can actually change the wheelbase number, and you can change the way it ends up. Okay, and it might not be this, since this is a PowerPoint, and I'm a little not that great at PowerPoint. The little curve at the exact end is not quite what I was trying to show. There is curve, kind of a continuous curve.
It's like an arc.
Yeah, like an arc. All right, so by changing the wheelbase number, you can kind of pretty much tune it into where it's going a straight line. Then you look again at the distance, and you say, okay, this is cool. Then when you get pretty close, then we're going to move to another step. And that is you should be able to put the robot on the table, give it the command to rotate. You know, you take your little thing and you put a piece of tape there. You say, rotate 5 times. And then ideally, when it comes around that last time, right on the money. Now, what you might find is that it's like this. Or it's like this. In which case, you can adjust the wheelbase number slightly, and hopefully you bring it back to here. Now, the next thing you do is you do it in the other direction. And you got it perfect this way. It's really working great. And you do it in the other direction, and all of a sudden it comes out like that. Okay. That's probably your hardware construction. You got something not quite aligned, something's not quite right. All right, so what do? Well, you can futz a little bit. Maybe you find this compromised value, or you can optimize it for one direction and then use that direction in your program.
Right?
Okay. Yeah, and that actually works pretty good. All right.
Well, or tune it for get a number for each left and right.
And
curve,
I've done that too. Thank you, Ron. That's also an adjustable, and you have to decide how much you want to futz with it to get it right, and you can. And it's not unusual. It's not unusual for them not to be perfect, but they'll be surprisingly close if you did a good, careful job.
So the it sounds like, you know, obviously you figured out wider wheelbase works better. Is there like a minimum encoder count per revolution that, you know, because if you...
This is real interesting. Duke and I, or Dick Swan and I, are great advocates of the higher the count, the better it is.
The better it is. Yeah.
Now, there's a point of diminishing returns. And the question would be is, if you had a choice between a 24 count per revolution or 1,000 count per revolution, I'd go with 1,000.
More is better.
Yeah. So the problem with surplus is that a lot of times you get these 24. You know those little micromotors you're using, not the micromotors, but those little Swiss motors?
Yeah.
They actually have a pretty nice, I believe they're
190 something.
Yeah, 191
or something.
And they're probably good. That's probably good enough. Like I say, the higher the number, there comes this point where it probably doesn't really matter.
Yeah.
Okay. All right. So there's a little bit of tuning. Oh my, I'm lost. All right.
Doug, can I suggest one other method of,
Sure.
of tuning?
Yeah.
Since the boys on their Lego robots always have basically line following capability,
Yeah.
they just created a course, calibration course that's just one straight line, and then off to the side there are red bars that a second optical encoder can check so that it starts following the line. That forces it to go straight regardless of differences in the tires. And then they start marking, they mark an initial position when they first detect the line, and then once they've gone a meter, then they they take another reading and they see what the difference is between the two motors.
What if you're oscillating? What if you're like generating kind of a sine curve? Wait a second.
Well, they have a
Going back
very,
and forth. I don't know.
Because, I mean, in other words, isn't that gonna have a longer length than the straight line?
well, they have a PID
So-
motor control,
No, but I'm-
line follower that is like, you don't see any waggle.
Okay, you don't see it, but I'm wondering if it would exist if you looked at the encoder counts. I wonder if you would see the PID controller generating just a real shallow sine wave. And so the length of that curve is longer than your straight trajectory. Just a thought. I mean, I don't know.
Yeah, but
It's a
you've
possibility,
used
but it's
it-
likely to be
But you
symmetric.
used it,
And-
Kareem,
Well,
you've
but-
used it and it works, right?
It works.
Okay, yeah, okay, for
Okay, that's the
differential.
ultimate-
Okay, for differential, okay.
Okay.
I was thinking absolute, never mind,
Okay,
sorry.
all right. And Kareem, I'd like to talk to you about that because I think I understand what you're saying, but it'd be cool to see that on a piece of paper, okay?
Sure.
Just drawn out.
Or even a video.
I think you have a video of that.
Okay,
Yeah, that's interesting.
I'm gonna have just a useful thing I found is
okay, okay.
long institutional hallways typically have 1 square foot tiles. And that's like a great big piece of graph paper. It's awful handy to do these kind of
I like
measurements.
wooden floors,
Same reason.
Yeah.
because they got a bar every 4 inches.
Exactly.
Okay, so, anyway, so in Can-Can, okay, in odometry, drifts are gonna occur. You can't make a perfect odometer. I mean, if you ran it for a day or two, it'd be totally lost. Running it for 10 minutes, no problem. I think Dave has probably done it for an hour, okay? So what I'm saying is you can do it, you can boost it with other sensors to make it accurate, but just on itself, with encoders, it'll eventually will drift off. But for this contest, it's not an issue, all right? If you build one, it will work. Except, you have to stay away from the walls in that opposing robot. But you can't, okay? Because they're going to be out there. So you need to have 2 things. One, you got to know if you're lost, and then you have to be able to reacquire your position. Okay. Now, I'm going to suggest a really simple way, and then kind of hint at some other ways that you could go. All right? You could, first of all, so the first thing you need to do is check periodically, and especially after an event. And what is an event? That means you hit the other robot. A good way to tell if you've hit that other robot is to have an accelerometer, which says, hey, something happened. I hit something. I don't know what it was, but I hit something. And that makes your odometry suspect. Because you don't want to spend the next 8 minutes, like wandering around in a circle. Okay, so you want to be able to reacquire that position. So this one describes a way that to do it. I'm going to show you that on the next foil, so let's not worry about it. Here we have a vision system with a camera. If you have a camera, you can actually use the count of pixels. You can set up a table saying, hey, if I'm looking at the goal, and I know it's 35 inches, it should be, if I'm at such and such a place, I should see so many pixels, a line of so many pixels from edge to edge. And that'll work until you get up so close to where it disappears off the edge of your screen. Before that happens, you can only find X by the offset from the center. So before it disappears off the screen, you may be offset and lose one end of it. And that way you can get some compensation by rotating around and taking a look at the other goal, since it's 35.2, and come back and say, okay, I know where I am, and go on from there. So that's one possibility. I don't think it's perfectly foolproof, but it's probably easy to set up. Now, for a person who doesn't have a camera system, and remember, this is a way, it's not the only way, but here's what's suggested. You take 2 sensors and you put them out like this. You know the distance between the walls. The X walls are contiguous all the way down the whole thing. All right? So you should be able to, and you know the distance. So if you're totally wrapped around the axle, You can spin until you start to see something like the addition of your two sensors plus your robot says, hey, yeah, I think I'm roughly in the right direction. And hopefully you're pointing at the right goal. That's another thing you've got to worry about. But you just wiggle a little bit until you get the minimum value. All right, now you know roughly where you are in the X direction. Now, drive over to a wall, 1.5 feet. All right, so now I'm 1.5 foot from the wall. My sensor should be telling me I'm 1.5 feet from the wall. And I now have a target in my Y direction. And so how I do is I rotate by 90 degrees and look those ways and see where I am. So that is a way. And I'm not sure it's the way, but it is a way, okay? So
that one's really susceptible to your opposing robot being in the line of sight.
And
no,
cans.
it's possible.
cans,
That's
yeah.
possible.
And cans might rotate around and find
No, well,
the
you
distance
use
between
the
two
cans. You can use this.
Just look over the
Use
top.
it, does
Look
that
over
mean
the top.
sideways, because can't they get knocked over?
You're not looking for cans. You're lost, and you're trying to find where you are. Now, Kareem's hit a good point. Is, you know, if you have a 15-foot robot walking by there, you're going to have a dead spot. Okay. But what's going to happen like that is you should see. Remember, you know how far the walls are. So if all of a sudden the wall's got like 2 feet shorter, you know the robot's in the way.
Something's in the way. Yeah.
Right, so you might want to scoot up a bit, okay? So, yes, the robot's in the way, it will cause an issue, and it's a good thing to know about, but I don't think it's an insurmountable issue. Okay?
No, you just repeat your process over time.
Yeah,
Make sure that it's-
Some other
Other
things that, other ideas that I didn't have time to completely go through, but is, you know, triangulation. That's where the problem with that, you got a goal out there that you know is 35 inches wide. And if you knew the interior angles of that to where you are, okay, because you can find your apex angle by saying, oh, I see this guy, and oh, I see that guy. But usually what they do is they on their reference point is they want those interior angles, and they use the law of cosines, which says that the side divided by the sine of the angle is always going to be equal. So the opposing angle to my side, that side length divided by that angle will always be equal, okay? So, to each other. So, you can use that and try, so I'm not giving up on this yet, but this may not work. You may be just missing one piece of information. Another possible way is parallax shift. Now this might be a computer vision solution. And this your camera would have to move somehow. All right? And what it does is it does the same thing as you do here. And if I were to go and mark where I think I see this guy, and then I close the other eye and it looks like it's gone over here, that distance is the parallax shift. And there is an equation for that that will give you the distance of the object.
Yeah, or the robot could move
Yeah.
to get parallel.
All right, so
Anyway.
there is another, I'm trying to be a little thought-provoking here. And then there's the old Lego square up on the wall thing, which will give you that you're orthogonal, but it won't necessarily tell you your X and your Y. Okay? But it is a good thing to keep in mind because you might want to make that part of your other strategy. Okay, now finding the target. All right. Let me drop out of here for a second and you've all, come on.
Just use recommended. Probably just have another
I don't have, I thought I had, what is it, V? What's the name of that?
Starts with a V.
Yeah, it starts with a V, but that's all I remember.
I know what you're talking about too.
Sorry I was late. My car needed 4 quarts of oil. I kind of forgot it. Burns oil, and I forgot to add oil.
Well, I hope that wasn't because, you didn't find out because it went, yeah.
Almost. Started making a lot of valve noise.
Okay. All right, I'm gonna hopefully be able to move this up. You've all seen this video, I hope. It's on our website, or was somewhere.
Yeah, they all burn oil.
No? That's interesting. All right. Maybe it'll come someday. I'm going to talk about 2 ways. You've probably all seen, if you've seen that video, you've seen the tabletop competition. And in the tabletop competition, there were 2 algorithms shown on how to go find a can. One was my way, where I had the little robot that went doo, 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 all the way around, and it came back, and then it would go and find the can very accurately. Would do it, drive up to the can, worked real good, slow, real slow. In fact, last competition, Ron's robot grabbed 2 cans, was running towards the base with the second can. He hadn't got the first one, he dropped it in the wall. And he keeps coming with the thing, and I'm still looking for my first can, and intercepted. So what I was doing was taking 3 measurements, using the middle measurement, because I was thinking there could be noise. I would rotate 10 degrees, and then I would check if all the angles, and when it's finished, I had a map of the distance of all objects within 10 degrees. And what you would see is where there was a can, that value would come closer than when there was no can. And then I would take those 2 angles and divide them in half, and that would be where my can was. Pretty classic. Now, what Ron was doing was he had an IR sharp sensor. He would run and he'd start moving, and then when so let's say this stand up, John, be a can. Okay, so when I'm looking out this way, I don't see a can, I don't see a can, I don't see a can, I say, oh, I got a can. Then I rotate to them and pick them up. Now that's good for 2 reasons. One, it's fast, but not only is it fast, but I was moving. Otherwise, when I detected them, I'd already gone part of the distance. So I didn't have to go as far. So I was double fast. All right, you can see. Good can, John.
Nicely done.
Okay, so this one to me looks like a superior algorithm. This one will work, and yeah, you could make it faster than that. You could use a servo to do the sweeping through a certain angle, but this one was really a pretty cool way of doing things.
I put the robot there.
Oh, okay.
Yeah, most of it.
This is the robot that did it. Okay. Very good. Now, okay. So I know where the can is. How do I move to it? Boy, this is starting to ask like a lot of questions, isn't it? All right. Well, you can turn if you know where where it is. You know 2 things about it. After you've detected it, you know the distance it is, and you know the angle it's at. In the case of Ron's algorithm, you're pointed right at it. All right? In my algorithm, it would drive to that right angle, and then it would do something called create a capture waypoint. And that is simply, says I want my x to be where I started in position, where I am right this moment, my x and y position, plus the distance to that particular can times the cosine of theta, because I'm going to take that distance and divide it into x and y components. So I now know the x and y value of the can. And I can make it a waypoint, and I can go drive to it. Okay? Now the other way you can do it is like I think Ron did it, was, you know, he saw it there, and he said it was a foot, so he drove a foot, and it was there. Okay, and you know, I assume it said a half foot and a quarter foot, and yeah, I'm there. But you, with a navigating robot, you can literally set a waypoint and drive right up to it. I mean, within a quarter of an inch, if you want to, and not actually make contact. Right. I hope this is giving you some thoughts for different ideas.
I have a question for Ron.
Okay.
Did you just assume when you saw the can to turn 90 degrees?
I can't remember.
Thank you.
Yeah, I think I had to calculate some deceleration, and I think I did target a point. I think I calculated a XY coordinate in my space. So.
Okay. All right. So, okay. Now we talked a little bit about creating a waypoint. What if the can's moving away from you? It's probably not the can. It's probably that other guy. So you might want to be able to get a way around him. All right. Now, if I'm going to take the case where he's essentially not moving. He's either moving into you, you're going to collide, or he's a fixed object. If he's moving across your path, I'm not taking that into account. You could calculate that, but that's not what this little piece is doing. So what it's doing is it's really going to create a temporary waypoint. But I'm going to make an imaginary waypoint. Otherwise, as I'm driving along, and John's in the way, just stay there, John. John's in the way. All right, I'm going to say, okay, at this point I want to turn left and I want to go to some point out here. So I know where my x and y is. I know the magnitude because I want to go a foot in this direction. So I use the same type of method that I used before to create an imaginary waypoint out here, even though there's nothing out there. I turn to it and I drive to it. Then I reload the original waypoint. Then I start heading back towards my original waypoint. So I went around. Now I did it in one step. Now what happens if I hit another obstacle? I turn this way, but dang it, there's something in the way again. I create another temporary waypoint. Go off. Or I might want to change the angle. You know, since I had that one, I probably can do this way again. I come out here. Now it doesn't matter how many times I do that. Okay, because I still know where my x and y is. And I'm just never getting to the waypoint that I'm doing because I'm getting something in front of me. And I have the original target stored. So when it comes back, I just drive to when I finally do reach my imaginary temporary waypoint, I just reload the original target and drive to it. So where would this be helpful? You got your can, you know the goal's over there. That's your target. You're going to go to that goal. Dang it, something got in my way. I want to go around it. This would be a way you could do that. Okay? Okay, now I'm getting close to the end. Staging actions. There are many, there's state machines. There's a lot of different ways of handling repetitive tasks. One thing that I've found, one structure that I've found that works for me because it's easy to modify, is this idea of the arena is a stage, and I'm putting on a play, and I have acts. When I get finished with Act 1, I'm going to move to Act 2. When I'm finished with Act 2, I'm going to move to Act 3. And we're going to look at a main.c here in a second, and you'll see how this works. But the idea, so like for tabletop, Act 1 might be push can over edge. Act 2 is push can into the box. Act 3 is take can to the starting area. And the stage manager function moves from act to act. I found this very easy to modify. All right. What does it look like? Here's an early example. In this case, it's just knocking 2 cans off the table. And I found since then that it's easier to put these guys in separate functions. So that way I just modify the little function. But in here you can see it goes and finds the object distance. It points at by using a point at object thing. It delays for a second because speed wasn't of the essence in this. It makes an object capture waypoint. Remember that was the routine we saw earlier. And then it constructs task 1 waypoints and goes to it. And then, so when the task stage moves to Act 2, it does the same thing because it's the same particular task. The thing that you note is that when it moves to task 3, that's stop at the end. This is just a way I found useful to organize things. Now here's a main, and a couple things here I wanted to share. First thing I do in main is I run a sensor check. I have a display. So the first thing in this particular robot, I would check my ultrasonic sensor. Then I would do a battery check. Then I would initialize my cliff sensors. Then I would test my cliff sensors. I actually see them on the little display telling me, yay, verily, there's, I look at the light and the dark readings. And then I select a path because my robot generally has multiple paths in it to allow me to do different things. I initialize the robot, and in this routine that simply says I set a wait state. I wait for a button to be pushed so that my robot, as soon as I turn it on, doesn't go nuts and start doing things. To go through each one of these, if you were to look at each one of these little routines, I have to push a button to move to the next one. When I go to the initialization, it sits there and says waiting. When I push the button again, it says start and then proceed. Okay. So if you look at this, if you go back and you look at the delta target subroutine, you'll see that the segment stays 0 unless you actually are at the target. So seg stays at 0. So the next thing I do is I measure my cliff sensors. I check for the starting area box because this is tabletop. Okay, I calculate X and Y target. That's from my waypoint list. If waypoint is equal to the last element, it says I'm into my last waypoint, so let's go ahead and move to the stop. It actually says to increment the task stage. And so the only way it gets here is if the segment equals 1, which only means that I've moved to the actual target. All right? Then I take my interval count between my two, I run my odometry, get my new X and Y, I do a locate target, I check calculation, that's motor control, I do my motor control loop, and I update my display if I'm using a display. And it just rotates through that over and over again. So that's a sample loop, and that's it. I hope this was useful. I'm hoping that the teams that are working on Can Soccer get something out of it. If nothing else, you should be able to do a navigating robot now. Okay, that's it. All right, Rob, you got a big boy in there?
Well, Will was sick, so I was sick too, but I guess I got better. But he did, so no shoulder.
No, do you
okay.
got?
Did you bring your?
Yeah,
okay.
Let's bring her in and show. So
okay.
Big robot.
Where are your slides going to be?
They'll be out on the web. I'll send out some to the
Okay.